Good afternoon and welcome. My name's Tommy White and I'm one of the developers of the Masterseries. The Masterseries is a system of structural design software for steel, concrete, masonry, timber, retaining walls, the whole ream of different materials. But today we're just going to look at steel design. We're not going to show you frame generation, it's just going to be how, once you've got your frame designed, one or two little bits you need to know about for steel design in the analysis, and then going through and designing different elements and whole frames. What I'll do is I'll just open up MasterFrame. The assumption will be throughout this webinar that you know how to use MasterFrame. And we'll just go to my little demo and just get that file. So this is my little steel frame that I've chosen. It's a plain frame just so that we can all see it quite clearly. It's got mixed construction, it's got bracing members, it's got pinned members, it's got partially fixed members, it's got partially fixed bases. These are all things that you learn about in our frame analysis webinars and training tutorials, so I'll not go into those too much. It's also got members that are sort of splitting each other, so that you would probably want to design that as one member, and we'll look about how to do that in a moment. It's also, when we move into 3D, got several different materials, and I've accidentally made that column the same as this one. I only wanted those three to be concrete, so I will just go and fix that one in a moment. We've also got cellular beams, we've got compound beams. If I just turn this into 3D, we'll see that we have here a beam coming into a column coming into a column, so it's a compound member. And we also have up here a member with a steel plate underneath. And of course at the top we have a little portal frame. And interestingly, just because this is a hangover frame from a steel frame analysis type tutorial, this column here, while it exists, doesn't provide any vertical or lateral support to this. So it's actually not doing anything. This apex will sink like a normal portal frame. So that's my basic sections. What sort of sections can we do? Well, let's look in more detail. And for steel design, obviously, we would look at our different types of sections. And as I mentioned, we've got our traditional UBs. We've got all our different materials, our flats, our round bars, our European sections, our hollow sections, our jumbo sections, our large hollow sections, angles, channels, parallel flange channels, split T's. They're all your standard geometric shapes. We also have, looking over here, a built-up section. This is a section made up 500 deep, 200 wide, top flange of 15, web of 10, and the bottom flange is the same as we put in 0. And we have no root fillets, which tells us that it is a plate girder, not a rolled section that I haven't got in my database. Looking at the compound section, you'll see that we just tell it that it is a cellular form beam with an S of 1.25, a D of 0.6, and fill in all the holes. So we get all the holes we require out of a 610 section. The plate on the bottom is very simple as well, and then we have our hinged members. So without further ado, I'm going to look at the loading. So I'll just turn off this and close this, and a very quick brief look at our loading. And the loading on the frame is all very straightforward, nothing too exciting. And if I go to all cases, I can see my dead loads, and I probably just need to magnify that, and my D1s, just magnify that slightly. So I have a few different loads, and I will see my live loads and then my wind loads from 0 degrees and wind loads at 180 degrees. So we're not really that interested in the loading. It's the steel design we're interested in. But one item of interest is if we look at the input of actual physical loading. I have also, I hope, put onto one of these members, and I believe it's this one, a torsional load. So I've taken my basic dead and live loads. I then have given it an eccentricity of 100. I put on an additional partial load that's sitting out off the shear center of the member, which will give us a rotation or torsion on our member. So because of that, I have to analyze this as a space frame rather than a plane frame. Now, the next stage is to look at loading cases. So loads, loading cases, loading combinations. Now, initially I am going to work with the BS code of practice because I do have a lot of people logged in today who are not from the UK, who will still be using the British codes. We will switch over to the Euro codes at some stage, but we will concentrate initially at the BS because you will all be more familiar with the BS anyway, and it's not that different. You will see there's small differences that will take effect. So loading cases, first of all, I have my ultimate limit state dead and live. I have my live only, dead plus wind, dead plus live plus wind, and then the repeat of the wind coming in the opposite direction because this is an asymmetrical frame. Now, those are all basic, and it's again, as I said earlier, covered in the frame analysis webinar. What I want to add into this, because this is a steel design, is I want to create notional horizontal loads. I want to create horizontal loads rather than size pick, and I want to do them at 0 and 180 and do it to the BS code. So I go from 6 to 10 loading cases. I end up with my ultimate dead plus live plus notional in both directions, and my sway stability in both directions as well. Just sway stability only. So we've got all those. I don't do P delta yet. I just do my notional loads. There's no point doing P delta until we've sized the frame, and at that point we can decide how flexible or rigid the frame is and whether it requires P delta analysis to be applied. There's no point making work for yourself, particularly when the frame's not been sized and the members may be so slender at the moment that it might be unstable under P delta, and you'd be chasing yourself rather than getting a structure that works and then testing it for P delta. So the P delta we will ignore, and the last thing I want to look at is a couple of super members before we go into the design. So geometry, super members. What are super members? Very simple. If you think about it, these two members are really one member. These two members are one, and these are one. There's no harm in making a single member a super member. It will not cause any real problems. That's the analysis super member. So those members will be a super member handled as one in the analysis for the loading, in the design, and in the drafting. Design super members, on the other hand, will not have any effect during analysis, but in the design they'll be considered to be one length, which makes that interesting. Concrete and steel, it will override and use the steel section. And then drafting super members. Drafting super members are really a little tool to let you say these three sections must be the same size, these two sections must be the same size, and it's very useful. So before we go and analyze, let's go and fix that little section property problem I had. I believe I had one of my columns, so I come back here, sections, section sizes, and this is the concrete column, and this thinks it is as well. So we'll take this section, or this one, I'll take this one, and I will just paste it onto these two members and make them steel as well and replace. So now if I go 3D, they look correct. So let's just analyze and get straight into our design. And because we put this eccentric load onto this beam, we would really need to analyze as a space frame. So just looking at the frame and just checking our output for 1 second, output, and it's graphical, and look at the bending moment diagrams. Just turn off the 3D profile and just reduce that scale down a bit. That's as we would expect. Some members simply supported as we stipulated, others partially fixed, others fully rigid, and others working concrete. The portalization that we get here with no uplift here because the column is not taking any axial load. If we look at the deflected shape and we just descale that, sorry, wrong way, we will see up it comes, and with the diagram we can see the movement that we're expecting. So we're getting what we expect. That's the first step. So we'll go straight through on into design. So design, steel design. And I'm going to do the design in 2-3 different ways. I'm going to take you up stage by stage. So first of all, we're going to look at some individual members and go in detail on those. And then we'll look at doing the whole frame. And then finally, we'll look at how the standard MasterFrame steel design is different when you actually have something called the 3D Model Manager applied. It makes your design process a lot quicker and more efficient. But we'll do it the standard way first. So we've come into our frame, we have nothing down here. Design brief 0 of 0. So we want a design check, and we want a beam and beam portion check, or standard check. Okay, it's created it, but it doesn't know where. We pick the member we want to apply it to. And here we go, we get our results. We get our capacity lines of the member, the 2 red lines. We get our bending moment, and we get our loading different envelope bending moments. We get a blue background because we've got a warning somewhere. And we get red tabs because we get warnings. So our local capacity is failing, our slenderness failing, our buckling's failing, and our deflection. So it hasn't got a lot going for it. So I need to choose a different section. Looking at my sections, I have my list of UBs, and that's where I am at the minute. So if I come up, say, to about here and try that, we're getting something a bit better. And you will notice that they're listed in serial order. So instead of serial order, I am going to go and sort by weight. So if I now drop the list again, they're now in weight order, so I can start and climb up quite quickly, because we're not getting very far with these, to maybe a 610, and we're still failing only just coming up. And there it works for local capacity, but it's failing under buckling because it doesn't know anything about the beam. It needs us to hold its hand. And we can do that by coming along and saying, well, actually, this member's got restraints. And it is, in fact, not restrained at the ends, but it could be restrained at 0.85L, or more realistically, restrained by the floor slab, and it's fully restrained. So we get this section that is our 610 by 113 kilogram UB as our solution. Naturally, if we chose a different grade of steel, we could possibly come back down again and try something a bit lighter, rolling up using the mouse just to scroll up 101. So we have saved ourselves there about 10% in weight by going to the higher grade of steel. Now that was very straightforward, but not that quick. Obviously we want to be a wee bit quicker. So what I can do is I can pull it right down to the bottom, a failing section, go back to my grade 275, and I can say auto size this member. So it will walk up with the criteria I've got and find the first section in the order that will work. So it's found my 113 kilogram 610 UB. Looking over on the right hand side here, it's about time to think about what we're seeing over here. And what we're seeing is purple members are members that are not relevant, they're not steelwork. Cyan members are members that haven't had anything done to them yet. So I just have this one member. Now I want to add another design check. So what I'm going to do is I'm going to copy this design check and apply it to this member as well. So I now have a second design brief on this member here, and I can quickly this time just say auto size, and I've sized that section. What I can actually do is with the copy, I could come along and I could do these here. So it's taking those members and I could do those ones there. And it's got all those, and I can now say, using the lightning bolt here, we've now got, if you watch the bottom, when I turn the lightning bolt, it goes from just one member auto size to a whole little tweaking facility. And I can now say, size me these members. Now if I go size these members individually, it's going to go and it's going to run through all the members that we just looked at, and it's going to size them up as best it can to make them all work, except for my castellated beam, which is pretty close but not exactly 100%, and it's probably not the design that's working but more the openings themselves that are problematic, and I would probably need to choose a bigger section. So it's not done that one totally because it really needs your hand to do that one totally, but all the other members have been done automatically. Now if I come up to my roof, we're dealing in a roof structure with, again, a simply supported beam, and again I can just quickly do that one as fully restrained if that's what I want, but probably not. The beam would not be fully restrained on the roof. It would be 1L, but it would then have portions, lateral restraints, at, for example, 1.5 meter lengths. So it's going to give me a portion there, a portion there, a portion there, and a portion there. So fully restrained, that member worked, but only restrained every 1500 millimeters. It's not going to work. So we need to do another auto design on that member, and now that works. So it's slightly heavier than would have previously worked. And I can now take that and I can copy that onto this, 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 and this. And then I can sort of say, well, let's get back here and have a look at this one. And I can say, okay, you give me a design for that one, and it's designed that one for me. And you give me this one, and it's designing this one, and this one. And I mustn't have put one on there. Oh, I did. I got it. And it's designed it, and it's just failing and no more. And sometimes it will stop at a very slight failure point to ask you to step in and decide whether it's so close to the bone that you would accept it or want a bigger size. And I think this one probably has no loading, and I'm just going to say no, that's far too small. Which brings me to another criteria. Not only can you design for lightest or shallowest, which is what we have here, you can set limits. So you could, for example, for this member, you could say that I only want anything that's greater than 200 deep. It doesn't know what to do, and I now go auto design, and it gives me a 254 by 102. Now in a 254 deep, a 102 is probably okay as a width of section, but sometimes you may say, well, no, I don't like those wee in old money 4-inch wide flanges. I never want to see anything less than 5. So we don't have that facility here on a member by member basis, but what we can do is go and filter out certain criteria. So looking at this, I can say for I sections I want a minimum width of 140, so I get the 146s, and I also want a minimum thickness of 10 mil and a minimum web of 6.3, which is probably going to be okay anyway. For my hollow sections, I'd want 6.3 for my wall thickness. So that I don't get any of the very, very tiny ones, and I would want a minimum size of hollow section of 70. So I've set some criteria, and as I close down that, go away and come back to this, you will see that when I auto design this member, it comes up with the 146 wide because the list has been reduced to only sections that obey those criteria. That is also very, very useful, and it allows you an additional degree of control. The one section we didn't look at in detail was this member here, and this member's got torsion on it. So we would look at this and ask it to actually design torsion. So it's finding the torsion, and it's now doing a design for the torsion, looking at the critical points, and we would have ends free to warp would be the traditional method of doing that, and we can see that this section with the torsion on it is still okay because the torsion isn't that high a load. Torque is only 6 kilonewton meters, which isn't that big. So we're able to do standard and quite complex designs. Coming back to our rafters in our portal frame, that's not the whole story. We really want to look at these with the hugging as well as the sagging to take account of this unrestrained flange length on this member. So we need to introduce a new type of design check, and that design check would be called, in the BS, Appendix G stability, and apply it to that member. And we then need to tell it where the torsional restraints are. So working from this end, we're going to go 3.6 and then another 3.6 and then another 3.6. So there's my first portion there and works, there's my second, and there's my third. So I would have a stay there and a stay there. Maybe I could get away here actually with saying this one was 7.2 and check this out, and over 7.2 length, that is not satisfactory. So it would be most sensible to put a stay every other purlin if we're dealing here with 1800 centers on our members, and that gives us our Appendix G. If you're looking for more detail on the Appendix G, you really want to look at our webinar on portal frame design. I'm dealing with mainly general frames here. So we've done all our beams. Maybe haven't done that one. So what I'll do is I'll go to this one and I'll copy this design check onto that member. And it looks okay, but we'll sort that out in a minute in another way. So now I want to look at my bracing, my 4 bracing members. So design check I would use for that would be something called either an axial with moment or a discontinuous strut and tie, as we can with the British code use using a more simplified method. And I would just take that and I would paste it onto that one, and that one. So these are all done. They're 150 by 10s, and would they actually work at that? Or yes, they do. Would they work a bit smaller? Let's see what we can get down to. And we can get down to 60 by 9. I would say 75 by 10 would sound a bit better to me, or 100 by 10. I'll try 75 by 10 would work, and you could try that on the bottom one, see what it does. Sorry, the wrong member. And again, it would work with a 40 by 4, 40 by 5. I would say 100 by 10. Choice is yours. Because again, we could have in here, and maybe that would have been sensible, set for flats, I want a minimum of 75, a maximum of 250, and a minimum of 10, a maximum of 25. So having done that, if I come back out here and I look at one of these members and auto design it, you'll see it's at 100 by 20. Obviously in the lower levels you get a higher load, and a 75 by 100. So we can use those parameters to design. So that's our bracing done. what's left are our columns. So the columns, we have some are fully rigid and some are just got members coming in pinned. So there's two different choices. You can either use the columns in simple construction, which is again a BS criteria, where you know everything's coming in pinned and it doesn't give any funny warnings about additional forces. And I would just copy that onto, say, this one and this one. There's our three columns set up. If I now go look at this one again, and I look at the one above it, it's working, but this one's not. So the section size for this one is the 46. Up here is a 46, and up here is a 46. If I now ask it to size this member, it comes a 52. That one becomes a 52 as well, because we said that these will be one member at drafting time, drafting super members. We size this one up and it still says the 46 because it wasn't part of the first two, and it can come down to 152 by 37 if you want. I can take that design check and apply that to these columns, to these columns, to this one, this one, this one, this one, and maybe even these. We've now got all our design checks on our members. So having done that, which we could have done very quickly without too much talking, and set up our basic parameters, we can use our different tools. We can now say, now go ahead and design all these members in one go. So it's looking at all the sections, all the members, and it's designing all the ones it can, and stopping at the ones it's just a wee bit unsure of. So it's now looking at all these apart from that one. So we can go through each member and design them. We can use this auto design to size each member up, and we can see everything works. We can also, having done that, if we have a frame that's not fully pinned like this one, which has got some rigidity, we would be sensible to reanalyze our modified frame and then scan for any members that fail due to the changes in loads, and it will find that 12 members now fail. This one's now got slightly failure, and I would just nudge that up. What I can do is ask it to size only the ones that failed, and it's doing those again, and now reanalyze, scan for failures, and hopefully we'll only get that one member, two members that have failed. So this column I was having problems with due to limitations, and I think it was this castellated beam just needs not to be a castellated beam really in that circumstances. The shearing is too high and it's a bit unhappy. But that gets us our general global picture of how we use this. Now, the next thing I want to look at is how do we speed this up a bit further if we're in MasterFrame and the steel design. And that is to use something called member viewing groups. If I just come back out, so exit from this and say yes, and now go into edit and geometry, sorry, viewing, I can create what we call member groups. And I've created one group called portal, that's very useful. I've created a second group called bracing, a third group called beams, and so I've created these three groups and they're member viewing groups. So reanalyze again, won't take long, not as a plane frame as you see, but as a space frame, design, steel design, and we will see now what we can do is we can ask it to display only that group of members, so we can highlight and work on that set of members at one time. So for example, I could choose in the viewing options, I get my little viewing panel here, and I go to member groups, member viewing groups, there we are, and I can say show me beams. So it's only going to show me all the beams, or I could say show me only bracing. So it's only showing me the bracing, and I'll just unpin that so that it hides when I don't need it. At this point in the design, I can go to my auto design and use not the second but the third one. So it's now going to say take these four members and auto design them all to be the same size. So it's going to say flats 275, yes, I'm happy, away it goes, and they're now all 75 by 12s, except one of them's not that happy at that. So it should really go up a wee bit. Oops, wrong direction. There we go. 120 would be satisfactory. But it does make my life a lot easier if I was to go back out and say, no, let's look at our beams. And then just look at the beams in this area. So what I would do is I would then window down just on those four. I could also say size those all to be the same. Now at the minute that's a 610, that's a cellular beam, that's a 686, and this is a 610. So by sizing them all as one size, UBs, it's actually decided to make them all the cellular beam, because that's what it's thought it should do. So I'm actually going to turn off the cell form, because I normally don't do this with a cell form beam. Make them all non-cell form. Oh, that was interesting. And now I resize them again. So now we find that the common section size for all of these is a 457191 by 161. So that's the shallowest. So it's 161 kilograms. If I redo them as lightest and say OK, they can back down to my 686s, but 121 kilograms. So a big saving in weight, but we're using over 200 millimeters of depth. I know which one the architect would prefer. So that's my sizing up of my member. So I've got a frame that now works, but what I now need to do is ascertain, as the second stage, do I need to look at sway stability, elastic critical load factors, and apply P delta. So having got a frame that's stable, and I will just turn off these viewing filters and make it back to the whole frame. What I would do is I would look at my elastic critical load factor. So what it's saying is, warning, we are finding quite sway sensitive frame, so we would require to use a P delta analysis. So it hasn't been done, it's saying we need it on. Warning and warning and warning. So let's get back, edit frame, save the changes, oh yes please, and go to analysis options, so options, analysis options, P delta analysis. Because this is a portalized type frame, I would be far happier using the Newton-Raphson. I'm going to turn it on, and then I will actually apply it to all my ultimate cases and say apply, and just go straight through and analyze that. Space frame please, design, steel design, and we would scan to see if that has caused any problems. So my auto design and scan for failures. It's going to run along and see what members are failing. 3 have failed due to these P deltas, so we got a little extra failing over just over here, and I can ask it to fix those members that are failing. So it's now fixed those, reanalyze, and this compound section is just a wee bit unhappy in simple construction, but I can go and manually fix that one little problem. Oh, analyze again, and it's now working. So there is my cycle of going through and doing my members, and just look at this elastic critical load factor, which is actually probably going to be down here as the last check anyway. And we'll see we got, oh, little values, yes, okay, enclad, blah blah, and it's given us a thumbs up on all the criteria. So our structure's been designed for these additional loads. Our structure's been deemed to be okay. Now, two things I want to look at, and then we'll do a quick questions and answers situation. One, I want to look at the Euro code. It's very, very similar, and I would actually go back to edit because it explains it better in here. Yes. Loads, loading cases, loading combinations. If you look, we have our standard 1.4s and 1.6s and things like that, and we have our standard dead plus live plus wins and things like that. So what I would ask it instead to do is the Eurocode equivalents. So we're going to get our 1.2s and 1.5s. We're going to get differences in it. We're going to get dead plus live plus wind at one point. We're going to get those reduced, so we have the dominant and the not so dominant loads, and we don't get separate notional loads on their own inside the Eurocode. That's all handled separately. So we just go through and analyze, space frame, design, steel design, and you would apply your checks the same way as I've just done, and you'd look at them the same way. And obviously, if we looked at this member, we get our beam and beam portion. Look at this one. We then have our appendix BB because it's using the Eurocode definitions and methodologies. So it's all working in the same fashion. So we would probably want to change those to be doing not in simple construction but just axial with moment, which we could do. We could add in new briefs for that. But I don't want to waste time. I want to show you how to do everything quicker and more efficiently. So let's just come out of this and pull in a different frame. And what this is using our area loading program. Now, with the area loading program, we get several advantages. Obviously, we put on area loading in our little frame. Obviously, if we have our wind analysis, we can apply wind loading on the frame. But that's not what I want to discuss. What I want to talk about is the facility with the area loading 3D model manager program. We get design groups, steel design groups. So we're able to predefine a lot of parameters. We're able to say, take all of these members, and we'll call them the strain beams, make them all fully restrained, and don't auto-restrain them. Apply nominal moments if it finds any something supporting. Don't do any torsion, and these are my limits. And we can also set up any portions if we need them, and our depths if you want to say minimum and maximum depths. So that's our restrained beams. More importantly, we can go for our unrestrained beams, and we can say they're unrestrained 1L, but we then auto restrain them, so this member will have a portion from there to there, from there to there, and there to there automatically. We don't need to know what the length of the member is. It will do that automatically. We then come along to the columns, and we're just going to go for simple construction, or we can just go for axial with moments. Let's just go for axial with moments just for the fun of it. And nominal moments is on, so if it finds simple support beams coming in, it will apply the additional nominal moment to the check. And then we have our bracing, in this case bracing 1 on one side and bracing 2 on a different side. So having done all that, and analysed. We come in to design, steel design, and it immediately creates all the design briefs for us. Now these ones down below are composite beams, so it's not happy about doing those, but the roof is all steel work. And you can see that it's got all the portions. And I don't need to worry about effective lengths or any of that because it's already done all that for me. And I just go and I ask for the whole structure, just go do your thing. And off it's going. And I obviously didn't save the file, so it's still doing those as columns in simple construction. And then sizing all the members. So I have taken 1/10 of the time to define all the design checks on a far larger frame using the 3D Model Manager as my holding hand, my helping hand. And the nice thing is that it knows what type to check to apply because we've told it, and it doesn't allow you to put a different one on so that it holds your hand just as you would expect it to. So it's now all working. Obviously we get these little small ones, so 3% over. We can ask it to auto size again, and at that it's just stopping and saying, well, you know, are you happy or do you want it bigger? So I just go and I'm going to say, let's just go up to the deeper one, and it's happy. So it's very, very quick. So in fact, shallowest auto design all is a more sensible method. Coming through, reanalyze all whoever cases, auto design them all again. I would always just do auto design, reanalyze twice by default before I start any investigations, so that the structure settles down. Reanalyzing for the second time, and now having done that, scan to see whether there's any problems, and there are some problems, and it could be due to our limits of section sizes that we'd stipulated. I don't think it is here. Strangely enough, it's not happy. Oh, we have hit the ceiling. We had limited. So that is how you do your steel design. And as I say, if you have the Model Manager and you're doing large structures, it's great. It saves you a lot of time, holds your hand. If you're doing small structures, the Model Manager will still save you time. I could, because I have the Model Manager, go back to my previous frame, even though I haven't done area loading. I can still use the member design groups. So if I went back to my demo file, I could come along, edit. Because I have a license, I'm perfectly entitled to come along and create member design groups. So I'm just going to say portal beams and make them active at the moment with Appendix G, and we will put portions at 1.5. I think we did, or no, we did 1.8. So that's those two members. So we just put those into the members and apply them. And then we add another group called beams, int for internal. Add all these. And then set my parameters. I can just say full restrained. That's all I want to do. Maximum depth 600, so that I don't infringe on the architect's ceiling heights. And I can then set another one up for the other. So I can still use this if I have the Model Manager license to speed up my steel design. So what I'm going to do now is I'm going to wrap this up, and I'm going to look at the questions that are here. see if there's any that need to be brought to my attention and to your attention. I'm going to have a wee look here. I see Martin has answered some very detailed questions. I wish to hear about the input of effective length under axial and moment. So we're talking about, well, we can do this here, because what I can do is I can come along and I can say, right, create another one that's called a, and I can say, let's put in this one. So if I'm dealing with simple construction, I don't have much here, but the effective lengths I would set in a column would be, say, 1 or 0.85 or 0.7 different directions. If I'm in axial with moments, a more general, I still have the facility to set kx and somewhere down the line ky. Now, if we go into the actual design, so let's just analyze this, get into it and have a wee look. Space frame, design, steel design. And we look at, say, one of these members. In here, we have our k factors, kx and ky, in simple construction. Very straightforward. If I look at the same button this time, I do a axial with moment on, say, for example, this member, I get a lot more data. And obviously, I have the kx and the ky and the lx and the ly. So the kx and the ky in a beam axial with moment still refer to the axial restraints. The lateral torsional buckling is separate and it is still handled by, this one. So you actually have 3 effective lengths in essence when you're dealing with a beam axial with moment. You have your bending and you have your axial, and whether this is a beam or a column, if we're doing a axial with moment check, you do have both of those criteria, and that can be different from this. So I think that covers that for you, Richard. It's very straightforward. Naturally, if you're dealing with a beam and you say had a restraint at this point and this point, so you have 2 restraints, so what length this member? Quickly turn on my lengths. My member is 8 meters long. I'm going to say the member is restrained at 2 meters and at 6 meters. So what I would do in this member is I would come along and put in lateral restraints at 2 meters. There's my first one. And at 6 meters. And at 2 meters. So I've got my first one. I can't add. It would be 2 and 4. So 2 and it's 4 meters. I can't add. That's better. It's the portion length. So it's 2 meters, 4 meters, and 2 meters. Now, the important thing is once you start to put any intermediate portions in, is you must make this into 1L. It can't be 0.75L, it has to be 1L, because an internal portion must be 1L for that portion. If it's fully restrained, there's no point doing these lateral restraints in the first place. You just go and make it fully restrained. Richard, I hope that answers your question, and thank you for joining us today. I know you're over there in Singapore. It's probably quite late at night for you. Any other questions, Martin, that I need to deal with? Okay, somebody's asking about points of contraflexure and a beam, and I think possibly for this I would probably want to go and look at a standard portal in MasterFrame. I'm actually going to generate one from scratch here just to show you how quickly it is done. I'm going to take a new a standard portal, number of bays, we'll keep it at 3 bays, we'll keep the basic loading, and we'll go for a partial fixity of 0, so pinned, and section sizes, and just analyze. Plane frame, output, graphical, bending, demagnify, up it comes. That's pretty normal. So we're dealing with these portions here where this is unrestrained. Let's go into design, steel design. Right, let's just look at the rafter. I'm going to assume that my purlins are 1800mm centers. So my first design check is going to be a beam and beam portion on that member. It's going to be 1L with lateral restraints every 1800. That's 1.8 meters. Now I don't need to tell it the remaining ones because it will say that it's very long and they will all be following repetition. Repeat, 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 repeat. So here we go. These are all my little portions. And of course that's totally valid for this portion and for this one and this one. But for here it's not really valid on its own. But we do leave it in, and I'll explain why in a moment. And I would probably feel happier going back to the British code so I don't contradict myself. That's okay, keep going. So my beam and beam portions. So now I introduce an appendix G check, as it's called in the BS, on the same member. And okay, let us imagine that we take it out to the end of the point of contraflexure. That's the default length. It is to the end of the point of contraflexure, and it's very unhappy. Just to make sure that's the case, if I say 10 meters, you'll see that it's to there. If I say 6 meters, it started to cut short. So the point of contraflexure is around 7 meters, 8 meters, but it will actually stop it at 7.362 meters. If I don't want to do that, but I want to always take it to a physical point, I would say in my options, not to check the point of contraflexure, but do the physical length I've asked for. So that becomes not 7.3, but 8 meters, because that's what I asked for. So clearly that's not working, and I need to put some stays to stabilize this unrestrained compression flange. So let's start at the beginning and try out at 3.6 meters. That will not work. So at 1.8 centers for my purlins, I can't get away with a stay only here. So I need to put a stay at 1.8, and I will try the next 3.6. And I will then go to that portion, and again that's not working. So again I will push the next portion back to 1.8, and I will now try the next portion at 3.6, and I will see, yes, that works. So stay there, and no stay in there, and that tells us where we have to put our stays. Now, but you're saying, but surely in this portion, when we look at the other design check, we're still checking, sorry, we're not in the appendix G yet. Just switch over to the other check. There we go. In this portion, surely we're assuming there's a restraint here which doesn't exist. Well, that's what the appendix G is all about. When you have an appendix G check, it says you then have to check each of these intermediate portions, pretending that they are restrained at each intermediate restraint. Even though it's not a torsional restraint, you still assume that. And that's why we always do this check anyway. And that covers it. Now, if you want more guidance, go into the user login area, log in with my credentials, go to technical notes, and under steel design 5950 appendix G usage, and we're just going to open the document and have a look, and it's over my other page. So here we go, 5950. This is the conservative method you would have done for years before we had appendix G. You would have designed for each of these compression flange restraints, and then to this compression flange restraint between there and there, and from this compression flange to here. Now, with 5950, we were able to say, well, actually, we can do, instead of a compression plus moment across there, we do an appendix G and appendix G, and then it says here the resistance to out of balance buckling between intermediate restraints, that's between here and here, or here and here, should be checked using an effective length equal to the spacing of these intermediate restraints. So that's why we do it. It tells you the belt to go with these braces is doing a compression plus moment or axial plus moment in each of these portions anyway. So just do them all the time, and that gives you the correct answers. And obviously this is wrong because you still need these braces of doing the compression plus moment, assuming that you and pretending that you had a torsional restraint at this point and at this point. So that's available on our technical notes. If you have any questions that haven't been answered, email us, either help at Masterseries or myself, Tommy at Masterseries, or Martin at Masterseries. It's all .co.uk. So ladies and gentlemen, thank you very much and goodbye.